So I'm happy to introduce Soudeh Ghasemian. She's a PhD candidate in my lab, and she comes to us with a bachelor's degree in natural resource engineering, specifically looking at dry and desert zones from the University of Masad in Iran, which she obtained in 2012. And in 2016, she earned a Master's of Science also in natural resource engineering from the University of Tehran in Iran. And since then, she has been a PhD student in my lab and advanced to candidacy last year, 2020, in the middle of a pandemic. And now she is, her dissertation is very broadly exploring sources of or drivers of variation in forest productivity across space. So she's looking at topographical variables and across time. So she does this using remote sensing data, going specifically looking at EVI as a proxy for forest productivity, going back in time to really very close to the beginning of the Landsat satellite program. And without further ado, I will mute myself, and Soudeh, you can take it away.
Okay, thank you, Sharon, and thank you everybody for joining today. So I should start sharing my screen. So just I want to confirm for another time, you are not seeing the presenter view, right, Ben? Perfect, thank you. Okay, so I would like to start with a brief summary about what we are doing. So we try to understand how climate modifies the influence of fine-scale topography and landscape position on forest productivity. Our research is about forest productivity and how it is affected by variations by different drivers. Forest productivity and its spatial and temporal variation are important because forests are key drivers of Earth's atmospheric CO2 concentration. There are different factors altering forest productivity, including water balance, plant competition, plant age, topographical features, climate, and several more that I just mentioned a few of them here. However, we will mostly focus on the effect of topographical features and climate on forest productivity. In this research, we will ask this question that to what extent topographical features, or like fine-scale topography and landscape positions, affect forest productivity as environmental conditions change. There are different ways to answer this question. We choose Enhanced Vegetation Index, EVI, as a proxy of productivity. EVI values were obtained from Landsat images with 30-meter to 30-meter resolution and from 1984 to 2017. We further obtained topographical feature values. Fine-scale topography, elevation, and aspect are assigned to each pixel based on a digital elevation model, or DEM, using light detection and ranging LiDAR. We use ArcMap and remote sensing applications to transfer raw satellite images into spatially explicit datasets. We likewise use our program to apply different models to these datasets, assessing the degree to which topographical factors influence forest productivity. You might ask this question that what is fine-scale topography and how it affects the spatial distribution of water and energy in a hillslope. To show the concept of fine-scale topography, if we consider the left figure as a hillslope forest, we can see a horizontal transect inside the red circle in the right figure. So the first tree inside the black circle is located on a convex topographical position, while the other tree inside the black circle is located on a concave topographical position. Local topography, like fine-scale topography, ranging in a scale from meters to tens of meters, can act as an important driver of forest productivity as it influences the spatial distribution of water and energy in a hillslope. We can see trees that are located in a convex topographical position inside the red circle and trees with concave topographical position inside the blue circle. Based on the location on a hill slope, soil can be wetter or drier, as trees can receive different amount of precipitation. Trees that are located down a slope receive more precipitation as water flow from upslope to the downslope. Topographical features influence the spatial distribution of energy as well. Vegetation on hill slope also can be energy limited like shady slopes or water limited like sunny slopes, a phenomenon that is more noticeable in regions with water stress. And another question here that how does landscape position affect the spatial distribution of water and energy in a hill slope? Fan et al. 2019 demonstrated in their research that there is a contrast of energy and water availability between northern and southern exposure. As all the study sites we've been working are located in the northern hemisphere, we likewise expect that regions with south-facing slope will receive more sun heat than regions with north-facing slope. This research has been conducted on 3 different forests across North America. Each of these study sites vary on 2 important drivers of forest productivity, moisture and energy availability. Their climate range from cold and wet like Morrisburg and Horseshoe Brook watersheds that they are located in Newfoundland, Labrador, Canada, to warm, temperate, and mesic like Holcomb's Branch watershed in South Carolina, USA, to continental with hot summer that typically experience moisture shortage late in the season like University of Kansas Field Station. Of the study sites, the forests located at the Newfoundland Labrador are on one end of the climate variation, while the forest located in Kansas, Kansas KU Field Station is at the other side. In this slide and the following, I wanted to demonstrate the different amount of precipitation and heat from the sun between these 2 very different types of forests. The continental temperate forests receive less precipitation compared to the mesic boreal forest, although it receives more heat from sun than the mesic boreal forest. In this research, we attempt to test 2 hypotheses on one of our study sites, the University of Kansas Field Station. The first hypothesis is based on the effect of a slope and climate on forest productivity. In a continental temperate forest like University of Kansas Field Station, upslope regions experience more water shortage than downslope regions, and this situation will be worse when the climate gets hot and dry. Therefore, we hypothesize that as climate changes to a hotter and drier condition, water stress will increase for trees in the upslope region, and this new condition will cause a reduction in productivity in such regions. The second hypothesis indicates that how the importance of both landscape position and fine-scale topography change as environmental conditions change too. In this schematic figure, we demonstrate the approximate amount of sun heat energy that is received by both north and south-facing slope in the northern hemisphere. And this hypothetical figure represents a hill slope with convex and concave topographical positions, showing how a concave position can become an advantage for a tree over time as environmental conditions change, air temperature, and therefore evapotranspiration increase from A to B. Before we go to the results section, I would want to define breakpoint. Breakpoint is associated with a significant shift in EVI value at certain elevation, and thus a statistical assessment of the slope before and after the breakpoint can reveal a complex relationship between EVI and elevation. In this schematic figure, breakpoint represents as a black dashed vertical line. To evaluate the extent to which the importance of fine-scale topography and landscape position differ, just excuse me, I wanna move the window of the person, the participants, and I'm trying to move it to the other side. Okay. So, to evaluate the extent to which the importance of fine-scale topography and landscape positions differ as the climate changes, we prepare several plots representing the relationship between EVI and elevation, colored by fine-scale topography. Concave pixels are shown as orange and convex pixels are shown as green. And we choose 1996 as a cold and wet year and 2017 as a hot and dry year to see how these forests respond to the environmental condition changes. When the climate gets hotter in 2017, productivity exhibits a sharp reduction at a slightly lower elevation as compared with a wetter climate in 1996 inside the blue circle. And this 1.2-meter decline in elevation at which the breakpoint occurred in 2017 was followed by a steeper decrease in productivity than in 1996. To begin test the second hypothesis, we selected the same years as we did to test the first hypothesis in order to investigate the degree to which the importance of fine-scale topography and landscape positions change as environmental conditions turn to a hot and dry climate. These plots show the relationship of EVI and elevation colored by aspect, and the blue points represent north-facing slope and the red points represent the south-facing slopes. As a climate gets hot and dry in 2017, trees located in wetter and shadier positions like concave position will have more access to retain soil moisture, and we observe an upward shift in productivity of trees in north-facing slope comparing to 1996. To continue testing the second hypothesis, let's get back to the previous plot showing the relationship between EVI and elevation. The convex points in 2017 are shown as like green color, exhibit higher productivity than they do in 1996. And this indicates fine-scale topography is not as sensitive a variable in governing productivity as the aspect. And as conclusion, we think elevation and aspect both become increasingly more important influences on forest productivity as environmental conditions change to hotter and drier conditions. However, the effect of fine-scale topography on forest productivity does not appear to be as sensitive to these changes in environmental conditions. And at the end, I would like to appreciate everybody that helped us doing this research, in particular Billings Lab and University of Kansas Field Station Award.